Realize the denominator of each fraction and express in the form a add bi. To realize it just means to make sure that we have the denominator as a real number, which means that we multiply both the numerator and denominator by the complex conjugate of the denominator. So this becomes 3 add I times 4 add 3i over 4 minus 3i, 4 add 3i. It's 12, 9i add 4i add 3i squared over 16 add 9, which becomes, this I squared is minus 1, so this becomes negative 3. Add that to 12 to give us 9, and we have 13i here, and this is over 25, which we write as 9 over 25, the real part, and the imaginary part is 13 over 25. Next we have 4i divided by 4 add I. So complex conjugate of the denominator is 4 minus I. So we have 4i times 4 minus I. And it's over 4 add I, 4 minus I, which gives us 16i minus 4i squared. It's over 16 add 1, which gives us 4i squared. I squared is negative 1, so that will be negative 1 times negative 4, which will give us positive 4. So we have 4 as the real part here, and this is added to 16i over 17, which we write as 4 over 17 real part added to 16 over 17 the imaginary part. Thanks for watching. I'm Alistair. Here we have another fraction to realise. Now remember, a complex number is made of the real part. Let's write it as the real part R added to the imaginary part. Actually, let's just write it using letters as A add BI. Now if we just have I, then A must have been 0, so we have 0 add B is, let's say, 1, and that would just give us 0 add I, which is I. Now the complex conjugate of I would be negative I. So that's our complex conjugate, and so we multiply both the numerator and denominator by negative I. So it's negative I into 3 add I over negative I times I. This gives us I minus I squared over minus I squared. Now I squared is minus 1, so in the denominator that'll be minus 1 times minus 1, which will give us 1. And here again, I squared is minus 1 times minus 1, which will give us 1. We always write the real part first, followed by the imaginary part. So we've just realised the denominator. The denominator happens to be 1, so we don't need to actually write that. Here we have a denominator of minus I, so the complex conjugate of minus I is positive I. So that's just I into minus 2, add 3i over minus I times I. Again, this will give us a denominator of 1 because we have I times I, which is I squared, which is negative 1 times negative 1, which will give us positive 1. So we can just look at the numerator and evaluate this. We have minus 2i, and then we have added to 3i squared. Now I squared is negative 1, and so now we'll have negative 3, and that's the real part. We always write that first, so it's negative 3 minus 2i. The real part being negative 3, and the imaginary part, negative 2. Thanks for watching. I'm Alistair. Here's our last question. 6 over x squared minus 2x add 10. We need to first find the complex factors of the denominator, and then we can work towards expressing this as partial fractions with complex linear denominators. So if we let the denominator, 6 squared minus 2x add 10 equal to 0, we apply the quadratic formula and we have two values of x, and these being 1 plus or minus 3i. The next thing we want to do is to find the complex factors, and they are for x squared minus 2x at 10. The complex factors are x minus 1 minus 3. If you're not sure about this, check my previous video and you'll see I've covered it in detail. X minus 1 add 3i. So since the required partial fractions for that have complex denominators, we must provide for the unknown numerators that are complex. And so we'll write that 6 over x squared minus 2x at 10, and this is our provision for it. We write these as complex numbers. X minus 1 minus 3i add c plus di, x minus 1 add 3i. And we can now write if we cross multiply in this direction, we have a add bi, x minus 1 add 3i, and c add di into x minus 1 minus 3i. And all of this over x squared minus 2x at 10. Now both the left hand side and the right hand side have a denominator of x squared minus 2x at 10, so we could eliminate that and just equate the left hand numerator, which is 6, to this numerator on the right. So we can write 6 is equivalent to a add bi. Let's give myself some more space on the right. 6 equivalent to a add bi brackets x minus 1 add 3i and c add di x minus 1 add, no, we made a mistake, this one is minus, yeah, minus 3i. Now when we have that x is equal to one of our solutions, 1 add 3i we'll choose. If we substitute here for x and also here, we eliminate a add bi, and we're left with 6 being equal to c add di brackets minus 6i, giving us 6d, the real part, minus 6ci. If we equate the real parts to imaginary parts, we only have a real part here of 6 on the left, and that's equal to 6d, so d must be equal to 1. There's no imaginary part, so c is equal to 0. When x is equal to 1 add 3i, we have that 6 is equal to a add bi times 6i, which gives us 6 minus 6b add 6ai. We have no imaginary part, so a is 0 and b is negative 1, because minus 6b is equal to 6, so b must be negative 1. So b is negative 1 and a is equal to 0. So now we can write, now that we have that a is equal to 0 and b negative 1, we can write that 6 over x squared minus 2x add 10 is equivalent to minus I over x minus 1 minus 3i added to I over x minus 1 add 3i. Now if you're wondering where is 1 and negative 1, it is here. This is negative 1 here. The coefficient of I multiplied by I will give us negative I, and 1 times I is I. Thanks for watching these videos. I'm Alistair. Bye for now. Hello. Express as partial fractions with complex linear denominators. So we've switched here now to complex numbers, but we can actually do all that we can do with real numbers. So first of all, let this denominator x squared minus 4x add 5 equal to 0. That implies that the solutions to this, I've used the formula, I'm not going to go through that again, is x is equal to 2 plus or minus I. Checking my previous videos, I've actually covered partial fractions for real numbers, and also just yesterday I've covered how to solve quadratic equations such as this one, where b squared minus 4ac is less than 0 or negative. So the factors of x squared minus 4x add 5 are x minus 2 add I and x minus 2 minus I. Again, here to get these factors, I've done a previous video just yesterday where I use the factor theorem, and I use this to determine the factors of this quadratic equation. Now we can write that x squared minus 4x add 5 is equivalent to x minus 2 minus I. brackets x minus 2 add I. Now for required partial fractions, the required partial fractions must have complex denominators. So we can provide, so that we can provide for complex numerators, we must write that 4 over x squared minus 4x add 5. Now we're going to write our complex numerators. Add this to c add di over x minus 2 add I. Now we can write that 4, well, let's write this line first, let's not skip this step. A add bi times this, x minus 2 add I, added to c add di times that in this denominator. C add di brackets x minus 2 minus I. And the denominator of all of this is x squared minus 4x add 5. Now because both the left and the right hand side had the same denominator, x squared minus 4x add 5, we can write that 4 is equivalent to a add bi x minus 2 add I added to c add di x minus 2 minus I. So when we have x is equal to one of these options, so we'll take the positive, so 2 add I, then this becomes 4 equivalent to c add, not equivalent but equal to c add di to minus 2I. So what I've done is substituted x is 2 add I in both here and here. In this case, it cancels. Is that correct? We have 2. Sorry, I made a mistake. It's 2 minus I here. So 2 minus I cancels with this minus 2 and 2 and minus I and I, which cancels to give us 0, so this gets eliminated. But this equates to negative 2I. And now we can write that this is equal to minus 2ci. Oh, let's write it with the real part first. It's 2d minus 2ci. Now if we equate, so if we equate real and imaginary parts, we have that, and we only have a real on the left, so we have 2d is equal to 4, which gives that d is equal to 2, and we have no imaginary parts, so c is equal to 0. Now when x is equal to 2 add I, we have 4 is equal to a add bi, and that's times 2i, which gives us minus 2b add 2ai. Therefore we have that a is equal to 0. We have no imaginary parts on the left. B is equal to negative 2. Because minus 2b is equal to 4. Therefore b must be negative 2. So we can write our original. Let's make some space for that. We have 4 over x squared minus 4x add 5 equivalent to minus 2i over x minus 2 minus I added to 2i over x minus 2 add I. Just to recap, we had that b was equal to negative 2. We had and d equal to 2. And we substituted those in those complex numerators in a previous part of this video. Thanks for watching. I'm Alistair. Bye for now. Hi. The same thing, but we have a different fraction here. 16 over x squared add 4x add 8. If we let this denominator x squared add 4x add 8 equal to 0, we use the formula and our solution or roots are minus 2 plus 2i and minus 2 minus 2i. Then we can write that 16 over x squared add 4x add 8 is equivalent to a add bi over x add 2 minus 2i. Check my previous videos. We've just applied the factor theorem to determine this complex denominator. Add c add di over x add 2 add 2i. You can write as a add bi x add 2 add 2i add c add di x add 2 minus 2i, and all of this over x squared add 4x add 8. We can eliminate both denominators because they're the same on both sides and write that 16 is equivalent to just the numerators. A add bi brackets x add 2 add 2i add c add di x add 2 minus 2i. Now when x is equal to one of these options, we'll take minus 2 add 2i. One of these will be eliminated. In this case it's a add bi, because this we replace x with this value. A add bi would be multiplied by 0, so it's eliminated. With that we have at 16 is equivalent to c add di times minus 4i is equal to 4d minus 4c. Oops, let's rewrite that. Equal to 4d minus 4ci. So this is the last line we're left with, 16 minus 4d minus 4ci. If we equate the real parts to the imaginary parts, we have that 16 is equal to 4di. There's no imaginary part, so c is 0. Sorry, 4d, not 4di. So d must be equal to 4, so we have d is equal to 4 and c is equal to 0. When x is equal to the other option, minus 2 minus 2i, we can write that 16 is, we eliminate c, add di, in this case add bi, and this is times 4i, which gives us minus 4b add 4ai. Again, if we equate the real parts, the imaginary parts, we have a real part 16, and on the right minus 4b, no imaginary part, so a is 0, but b is negative 4. A is equal to 0. Now with two values, constants, b equal to minus 4 and d is equal to 4, c and d are 0, we can write that 16 over x squared add 4x add 8 is equivalent to minus 4i. Oh, my mistake again. We have 4i over x add 2 add 2i minus 4i over x add 2 add 2i. It's just conventional to write the real part first, followed by the imaginary part. Thanks for watching. I'm Alistair.